Welcome back. This will be a video lecture on section 3.3 from the textbook, Constructing Bootstrap Confidence Intervals. I've broken this section up into two subsections. We're going to do a brief review. This will allow us to remind ourselves of where we're coming from and what the essential problem is. And then I'll show you how we'll overcome this problem through a process called bootstrap sampling. So let's remind ourselves of what we've been doing. We're trying to estimate a parameter within a population. And so far we've been building what are called confidence intervals, in particular 95% confidence intervals. And this is the method that we've been using so far, right? If we can first estimate the SE of the sampling distribution, and two, if the sampling distribution is relatively symmetric and bell-shaped, then a 95% confidence interval can be estimated using parameter equals statistic plus or minus 2 times the standard error, or equivalently, parameter equals best estimate plus or minus 2 times the standard error. In both cases, our statistic or our best estimate forms the center of our confidence interval, and the radius of our confidence interval is given by 2 times the standard error. That's also called 2 times the standard error, in this case, is also called the margin of error. Now, let's think about the problem that's inherent in trying to work with this formula. So in order to compute a confidence interval to estimate a parameter, we really need two pieces of information. We need the best estimate, and we need the standard error. Now let's think about the sources of those pieces of information. The best estimate can be obtained just from the sample. We compute the statistic from the sample that we've retrieved. Now, in order to get the value of SE, either it has to be given to us, or we have to build it up by continuing to resample from the population. This is what's called the sampling distribution. We've seen some examples of this where we're able to go in and draw sample after sample after sample out of the population. We're able to compute the best estimate from each of those samples, and we can build up this massive dot plot that shows us the variety of the ways that this best estimate plays out from continuing to draw sample after sample after sample. Then we can go up here and have StatKey just tell us what is the standard error that's inherent within this dot plot. So there's two ways that we can get the standard error. We can either have it given to us, or we can try to build it up by continually resampling from a parent population. So let's think about the problem that we face. In most cases, we only have one sample. We don't have the sampling distribution. So here's the question. Generating lots of samples from a population is very difficult, time-consuming, and costly. How can we estimate the SE when we only have one sample? Now here's the intriguing answer. We will use the one sample to create a new population from which we can resample using a computer. It's easy, it's cheap, and it's effective. And this technique goes by the name of bootstrap sampling. So what is bootstrap sampling? In principle, it's a rather simple idea. We have our original sample. Let's say it consists of these 6 characters. Now, we make a copy of that original sample, and we paste it repeatedly, in effect forming a large, practically infinite population, which we will call the bootstrap population. Now that we have our bootstrap population developed, we can repeatedly sample from this bootstrap population, and in this way develop the sampling distribution. Now, to make this concrete, imagine that our original sample was of size 6. What we're going to do is go into this bootstrap population and repeatedly pull out samples of size 6. For each sample, we will compute the corresponding statistic, or the statistic of record, and we can imagine putting that into a dot plot. And then by doing this process repeatedly, we can develop this dot plot, which represents the sampling distribution. Now, instead of this corresponding to the sampling distribution for samples drawn from the original population, this is a sampling distribution for samples drawn from the bootstrap population. Nonetheless, from that sampling distribution, we can compute the standard error, and this standard error can be now used in calculating confidence intervals. Sampling from our bootstrap population is equivalent to doing what's called sampling with replacement from our original sample. Let's look at this in the context of the figure that we have in front of us. Imagine that our original sample consisted of these 6 characters. Now, I want to form another sample of size 6 from this original sample, but this time doing sampling with replacement. So on step 1, I would randomly choose one of these 6 characters. Perhaps I'd choose this one. So I imagine setting that one aside temporarily, making a copy of it, and then tossing this character back into the mix. On the second trial, I would reach in and randomly select one of these 6 characters. Now, there is the possibility that I will select this same character a second time. That's possible. So I select one of these characters, bring them out, make a copy of them, put them back in. And I continue to do this until I collect a sample of size 6. That's called sampling with replacement. And so just to reiterate this, sampling from the bootstrap population is equivalent to doing sampling with replacement from the original sample. So conceptually, it is helpful to think of the bootstrap population and sampling from it, but it turns out mechanically it is the same thing as just sampling with replacement from the original sample. Now, to help us understand this connection between sampling from the bootstrap population and sampling with replacement from the original sample, let's consider the following problem. So, the following sample of size 8 was collected. Here it is. Let's think of this set of 8 elements as our sample that we collected. Which of the following could be a bootstrap sample? Now, there's 2 things that we want to understand, right? Since this sample has 8 elements, our bootstrap samples must also consist of 8 elements. And since this set only contains 1s, 2s, 3s, 5s, 6s, and 8s, those are the only things that can appear in our bootstrap samples. Okay, so let's take a look at the first one, right? Could this set be a bootstrap sample? Well, it consists of 8 elements, and if you look at the variety of things that are appearing in that set, I only see 1s, 2s, 3s, 5s, 6s, and 8s. So this is a possible bootstrap sample. How about this set here that consists only of 2s? Is that a bootstrap sample? Well, let's check. It's got 8 elements, so that part is correct. And does it consist only of elements from 1, 2, 3, 5, 6, and 8? In fact, it does, right? It consists of all 2s. Now, I put this example in there to remind you that that is a possible bootstrap sample. Remember, when we sample with replacement, we could select a 2, but we would put that 2 back in, and we could resample that same 2 a second time. In fact, what happened here was that element 2 got chosen each and every time that we reached back into the original sample to draw out the next element. So in fact, this is a valid bootstrap sample. All right, what about this next one? Well, it consists of 8 elements, and that's fine. So far, so good. Does it only consist of the elements that we see in our set here? And when we look at this, we can see, in fact, that this number 4 is not an element in our original sample, and therefore it cannot be appearing in any valid bootstrap sample. Okay. Finally, in this last one, we see that the set has 8 elements, which is great, and the variety of elements that we see appearing here, we see a 1, a 2, a 3, and a 5. Those are all elements that appear in our original sample, and so this, in fact, is a valid bootstrap sample. So we can see, just reviewing these 4 cases, this was the only case number 3, that was not a valid bootstrap sample, and that's because of the presence of that number 4 in the sample. That that's not appearing in our original sample, and therefore that's an invalid bootstrap sample. Now, hopefully by studying these cases, you can see the variety of ways that a bootstrap sample could look given the makeup of the original sample. I want to work some examples with you where we use StatKey to help us build these bootstrap sampling distributions and develop some confidence intervals. So in this first problem, we're trying to answer the question, what is the proportion of peanuts in a can of mixed nuts? So we're going to go to StatKey. We're going to go to confidence interval for a proportion, and we're going to look at the example called mixed nuts, count of peanuts. We're going to develop a 95% confidence interval for the proportion of peanuts in the jar based on a sample that was drawn. Let's take a look at this. So we go to StatKey, bootstrap confidence intervals, confidence interval for a single proportion, and we're interested in the file called mixed nuts, counts of peanuts. So there we are. We're all set. Now, what are we seeing here? The first thing we want to concentrate on is what's called the original sample. In the original sample, there were 52 peanuts in a sample of size 100. That gives us a proportion of p hat equals 0.52. Now, as it stands, that is our best estimate for that parameter within the parent population. Okay? Now, what we're going to do, I'm going to show you this by first generating some small examples. Let's just generate a sample. When we generate a sample, we're going to go into our original sample, and we're going to sample with replacement 100 times. Now, when we did this, we came out with exactly the same count, 52 peanuts out of a sample of size 100. That's a proportion p hat of 0.52, and that's plotted down here. When we generate another sample, we find that this time we got 59 peanuts out of a sample of size 100, and that gives us a proportion of 0.59, and that gets plotted here. Now, this is going to continue. Each time we're generating another sample, we're just sampling with replacement from this original sample. We're creating a bootstrap sample. We're calculating a new value of p hat, and we're plotting it in the dot plot. Let's reset this, and let's just generate samples thousands at a time. Okay? So this is our so-called bootstrap sampling distribution, right? This is going to stand in place of the sampling distribution from the original population. All right, we're using our bootstrap population instead. Nonetheless, the main thing that we can get from this is that we can now go over here and get the standard error that's associated with this bootstrap dot plot. That's going to be our SE. So we're going to want to make note of that. Our SE is equal to 0.050, and our best estimate, our p hat, pertains to our original sample, which is 0.52. To finish calculating our confidence interval, we just have to do a couple of simple calculations. We need to take our 0.52, and we need to add 2 times SE. And we need to take that same calculation. Let me just copy and paste, and this time with a minus sign. And so our confidence interval, our 95% confidence interval, is going to extend from 0.42 up to 0.62. So we have 95% confidence that the interval from 0.42 to 0.62 contains or covers the true proportion of peanuts in mixed nuts. Okay? Now, that's how we can calculate this confidence interval using the best estimate plus 2 times SE method. Now, there is one other way we can do this, and we'll see how this agrees. We can also ask StatKey to carve out the middle 95% of this dot plot for us, and we can see the range on the x-axis, the interval that covers the middle 95%. That should coincide very nicely with our computed confidence interval. So when I hit toTail, we are getting the middle 95% of the data is carried between 0.42 and 0.62. In this case, it coincides exactly with our calculation using the best estimate plus 2 times SE method. So no matter if we just have StatKey do the counts for us, Or if we use our formula, our master formula involving the standard error and our best estimate, in either case, we see that our 95% confidence interval extends from 0.42 to 0.62. Okay, I want us to take a look at a couple more examples. For our next problem, we're going to try to develop a confidence interval for a mean. So we're trying to answer the question, what is the mean rent for an apartment in Manhattan? So we're going to load stat key. We're going to go to confidence interval for a mean, median, or standard deviation. And we're going to load the file called Manhattan Apartments, parentheses, rent. So the rents from a random sample of 20 apartments were collected. And we want to develop a 95% confidence interval for the mean rent of an apartment in Manhattan based on that sample using this bootstrapping method. So let's go to stat key. We want to be in the bootstrap confidence interval section. In this case, we're doing a confidence interval for a mean. And we want to make sure we load the file Manhattan Apartments rent. And it's always good just to kind of get comfortable with what's going on here to look at the original sample. So here you can see dots that represent a range of apartment rents from across a random sample of 20 apartments in Manhattan. So you can see on the low end, there are rents that are on the order of almost $2,000 a month, up to some apartments that are close to $7,800 a month. So there's a range of rents that are being observed in this sample of size 20. Now, what is a bootstrap sample going to look like? Well, we're going to go into this sample of size 20 and we're going to sample with replacement from this original sample until we've accumulated 20 elements in our bootstrap sample. So let me just do one sample. So we're sampling with replacement. We're dropping those 20 dots down here. We're calculating the average of this bootstrap sample, and we're seeing that that bootstrap sample has an average of $2,966.65, and that average price, or that X bar, is being plotted in our dot plot. If we generate another sample, another set of 20 dots is being selected, and its average, or X bar, is being calculated at $3,108.25. And now we have both of those samples represented in our dot plot and their collective average, which is now currently sitting at $3,037.45. Now, we can continue to do this over and over and over again, and in the course of doing this, we'll build up a dot plot that represents all the varieties, all the ways in which bootstrap samples could be chosen, and how their corresponding X bar values will come out. So let's reset the plot, and let's just imagine doing this repeatedly thousands of times. Okay? Now what's emerging is this bell-shaped curve, okay? And the one piece of information that we really want to get from this is what is the standard error of this dot plot. And there it is. It's 301.342. So we're going to write that down and bring that with us for the rest of our calculations. So the SE is 301.342. Our best estimate is the original mean. So we're saying our best estimate for the monthly rent in a Manhattan is $3,156.50, let's say. And our standard error is 301.342. Just having those two pieces of information, we can now do the arithmetic to calculate the left and right endpoints of our confidence interval. So let's go over here and let's take our best estimate, our 3156.50, and let's say we'll add on 2 times our SE. Our SE was computed as 301.342. So one of our endpoints, our upper endpoint, is going to be 3,759.184. Let's get our other endpoint. We'll get this by putting the minus sign between these two. And so we can see our range is going to go from, on the lower end, 2,553.816 up to 3,759.184. So we are 95% confident, right, that the interval from 2,553.816 to 3,759.184 covers the true average price of an apartment in Manhattan. Now, let me just show you an alternative way to do this is just to have StatKey carve out the middle 95% of the data. And when StatKey does this calculation, we can see that StatKey is calculating a left endpoint of 2,642.9. That compares somewhat with our 2,553. And at the other endpoint is getting 3,807.35. And we're getting something that's close to that. All right. So these are not expected to be right on because these are slightly different methods for computing the confidence interval, but we would attribute 95% confidence to both of these calculations, either by direct count, as in this method here, or by using our best estimate plus 2 times SE, plus or minus 2 times SE. Okay, so either way we can see how a 95% confidence interval could be generated to solve this problem. Okay, I've got one more problem of this type that I want to show you, so let's go to that. So for our last problem, we're going to develop a confidence interval for a difference in means. And the problem we're considering is the question, do men exercise more than women? We're going to load StatKey. We're going to go to confidence interval for a difference in means, and we're going to look at the file called exercise hours male minus female. Now what we're going to see is that random samples of 20 men and 30 women were collected, and their number of hours of exercise per week were recorded. So we'll take a look at that data in just a second in StatKey. What we want to do is develop a 95% confidence interval for the difference in the means of the hours of exercise for men and women. So let's go to StatKey and take a look at that file. And we can see in StatKey that when we get to confidence interval for a difference in means, that the exercise hours file is the default file. Now, before we start generating the sampling distribution, the bootstrap sampling distribution, let's take a look at the original sample just so we can kind of get comfortable with what's going on here. So the data is split into the male category and the female category, and you can see that StatKey is using subscripts to denote the different groups. And so what you need to know is that even though the females are listed on top and the males on the bottom, the males are category 1 and the females are category 2. So all subscripts that refer to the males are the 1 subscripts, and subscripts that refer to the women are the 2 subscripts. So we can see the sample sizes here are 20 and 30 respectively. And we can see that for the men, the exercise hours are ranging from the low end of 2 hours per week to the high end of 30 hours per week. But for the men, on average, it's 12.4 hours of exercise per week. For the women, we can see on the low end of no exercise per week to up to 34 hours of exercise per week. But for the women, the average is 9.4. Okay, now when we look at the difference in those sample means, we're going to get 12.4 minus 9.4. So x1 bar minus x2 bar is that 3. That's the 12.4 minus the 9.4. Okay, so that would be, if someone asked you, what's your best estimate for the difference in the number of hours of exercise, you'd say, my best estimate based on this sample is 3 hours of exercise per week. That's the difference in the means. Okay, now, when we generate one sample, we have to see what StatKey is going to do. All right? What it's doing is it's sampling with replacement from the male dots. It's sampling with replacement from the female dots. It's collecting those samples below, and it's computing the means for those 2 samples. So we're getting, in this case, in this sample, we got 11.95 for the men and we got 10.23 for the women, and now we can see the difference in the sample means is 1.72. That 1.72 is then graphed over here as a dot, and each time we generate a new sample, it's pulling down 30 dots for the women with replacement, 20 of these dots for men, again with replacement. The sample means are being calculated, and the differences in the sample means are being plotted. So this is a fairly large difference. These two samples differ by 7.13. You can see what's going to go on. This kind of procedure can go on and on and on and on. Every time we generate a new sample for the men and a new sample for the women, we can compute the sample means and calculate their differences. So let's reset the plot. And let's just see what happens if we let this process continue for several thousands of iterations. So we can generate thousands and thousands of samples of differences in means. And after generating 5,000 of these, we can see that the dot plot is centered as it should be on that 3, right? That's our best estimate. It's centered on our best estimate. The thing that we really want, of course, is the standard error. And we should write this down and take this with us. The standard error is 2.354. Okay, so I'm going to write that down, and I'm going to keep track of our best estimate, which is 3. And so when we develop our confidence interval, we're just going to do the usual thing. We're going to take our best estimate, and we'll do plus 2 times the standard error, which was 2.354. Okay, that gives us one endpoint. I'm going to copy, paste, put a minus sign, and that gives me the other endpoint. So I can see my confidence interval is going to extend from negative 1.708 to 7.708. So we are 95% confident that the difference in exercise hours between men and women, right, is covered or is contained in the interval from negative 1.708 to 7.708. All right. Now, that's one way to do this calculation using our master formula. And the other thing we can have StatKey do is just simply carve out the middle 95% for us. And by this calculation, our 95% confidence interval will run from negative 1 point, let's call it negative 1.7 up to 7.6. And you can see that that agrees fairly nicely with our calculation from our formula. Okay, so no matter if you do it by the best estimate plus 2 times SE method, or you do it by having StatKey count for you and carve out the middle 95%, either way, you're getting your 95% confidence interval, in this case for the difference in means. Okay, let's go back to the class notes. Now, before we leave this section, let's briefly review what it is that we've done. Okay, remember our goal all along has been to estimate parameters that sit within populations. And in the last 2 sections, we've been developing the concept of the confidence interval, in particular the 95% confidence interval. Now, if we start here in the lower left-hand corner, we'll remember that a parameter can be located in a confidence interval that's of the form best estimate plus or minus 2 times the standard error of the sampling distribution. So there are essentially 2 things that we need to know in order to calculate a confidence interval, and that is the best estimate, and the other is the SE of the sampling distribution. So let's begin up here. We collect our sample, and from that sample, the very first thing that we can get, and the thing that is relatively easy to get, is our best estimate. That might be a p-hat, or it might be an x-bar. It's a relatively simple calculation, and so we've got one piece of our puzzle already filled out, and that is our best estimate. The next thing we need is the SE. Now, getting our hands on a sampling distribution is very, very hard, and instead what we've learned in this section is we can create from the sample a bootstrap population that we can sample from. So by sampling from this bootstrap population, we can develop a sampling distribution. All right, now we can get the SE of the bootstrap dot plot of the sampling distribution by looking at our display in this upper right-hand corner, so we can read that right out of StatKey. So now that we've got our best estimate from our sample and the SE from the bootstrap dot plot of the sampling distribution, we can put all those pieces together and form the 95% confidence interval for our parameter. We saw several examples of this. Now, I hope that that will give you some insight into how we can develop these 95% confidence intervals using this idea of the bootstrap. All right, I will see you for our next video lecture on section 3.4. Until then, take care.